Okay, great. Thank you very much. Thank you everyone for coming along and to hear about dark matter. So to give a bit of an overview for the talk, so the title's Mining the Invisible. So we're going to start off talking about really small things, and then we're going to talk about really, really big things in space, and then talk about really, really small things again, and then somehow we'll end up underground in Yorkshire. So bear with me, and hopefully we'll end up there. So I think before we can talk about dark matter, what we really need to do first is talk about matter. So what is matter? So I asked one of my year 2 students here in Birmingham, what is matter? And they said it's just stuff. So I thought that was a good answer. So it's on the slide. So it's just stuff, right? It's the stuff that makes up you, me, the table, everything we're familiar with. Okay. But how do we know that matter's really there? We can sense it. So I can touch this table. So I'm convinced the table's there. I can see it. I can see all of you sat there. Some forms of matter are a bit harder to detect. So, for instance, the idea of the air, I can kind of feel it if I move my hand quickly, but direct detection of it's a bit tough. So we can use indirect detection. So I can put a windsock and I can see the effect of the air blowing through, right? If we go to more fundamental forms of matter, much smaller forms of matter, then it gets a bit more tough. So there we need things like the Large Hadron Collider at CERN, which smashes together particles at very high energies, so we can probe the really small building blocks that make up the matter all around us, right? And so in this way, using experiments like this and many others, we've, as particle physicists, put together what we call the standard model of particle physics. So this is a list of particles which make up all the known visible universe that we can see, including the table, you, me, all of that. So this model is great. It explains, as I said, pretty much everything we can see around us. And as I said, it's made up of tiny particles. How tiny are we talking? So everyone's probably, well, maybe it was dark. Hopefully it was lit up in nice colors tonight. But maybe you saw Old Joe when you were coming in. So Old Joe is 100 meters tall. Okay. Old Joe is made up of bricks, which are about 20 centimeters big. Bricks, if I ground them down, are made up of dust, sand, let's say it's a millimeter in size. Okay. We can go much smaller than that, though. Inside each grain of sand is billions and billions of atoms. Okay. Can we go smaller than atoms? Yes, we can. Inside the atom, we have protons and neutrons, and even inside the protons and neutrons, we have smaller particles again called quarks. So we're down to really, really small sizes now, down to, this is 1 after 15 zeros after the decimal place. So that's when we say small, this is how small we're talking for the size of a proton or a neutron, let's say. Okay, so these, as I said, these are the particles we know about, make up you, me, and everything we can see in the universe. How do we detect these kind of small things? So these really small things themselves are pretty hard to observe. So generally what we do is we look at the way they disturb the matter around them. So you can think of that about in the same way as looking at footprints in the sand. So can anyone shout out what made these footprints in the sand? Human. A human. Okay, I heard a human over there. Okay, that one was easy. This one, that one's a bit more hard. Dog? Horse? Someone else? Any others? Cat? Okay, I heard cat, so this one's actually a cat. Okay. What about this one? This one's the really challenging one. Oh, I haven't got it first time. Everyone always says goat. So, no, it's a camel. So, yeah, first time, bingo. So, yeah, so we can't observe, we're not observing these animals directly here, right? But we're seeing the trace they left behind in some matter that we can observe. And this is kind of like how we detect these really tiny particles. To show it a bit more visually, this is what's called a cloud chamber. So in this chamber is a radioactive source, which is shooting out alpha particles, high-energy electrons, and it's causing basically condensation in tracks, which is what you can see here. So in a similar way to looking at the sand, this is a really visual way of looking at particles. Okay. So this is how we'd observe all these standard particles that we know about and we love and make of us, okay, in the universe we see. So this standard model is fantastic. It really explains everything that we kind of see to very, very high precision. Actually, for many particle physicists, they're quite annoyingly high precision. But we do know that this is only the tip of the iceberg. So we have some hints from our observations of the universe that actually this doesn't account for everything, all the matter in the universe. And actually, as we'll find now when we discuss some of the bits of evidence we have out there, this ordinary matter that comes from the standard model only accounts for around 17% of the mass in the universe. The rest of it is what's called dark matter. Okay. So we'll come to how we know this in the next few slides. So one of the first bits of evidence for dark matter was when observations were made of the rotation of these spiral galaxies. So you can see here is a spiral galaxy. And what people did is we have our theories of gravity. So we know how much mass is in this thing. So we can calculate roughly how fast we expect things to be moving as we go out into these spiral arms further from the center. So we kind of expect that the velocity of things, the way that the speed they're moving around, drops off as we go to larger distances. So that's what we'd expect to see. So something like that, if we followed a particular star here, it would move around like that. That's not, in fact, what we do see, though. What we see is that as we go to higher radius, things actually still move pretty fast, actually almost at a constant velocity. So going out here, things are still moving very fast. And what this implies is a bit of a conundrum, because we wouldn't expect this star to be moving that fast with that amount of mass in it. So this leads us to the conclusion that, in fact, there must be more mass hidden in this galaxy that we don't see in these bright stars that you can see there. And this gives us the idea of what's called the dark matter halo. So surrounding a galaxy, we expect there to be some halo, some spherical ball of dark matter, which is sat there, which makes up most of the mass. Okay, so this was one of the first bits of evidence for dark matter, not the first, but one of the first. Another bit we can think about is what's called gravitational lensing. So to discuss this, we're going to have a small demonstration, which hopefully will work. It works. So for this, I need a volunteer, though. So do I have a volunteer to be dark matter? Go on, then. Well, are we volunteering? I can have two volunteers. No. You want to volunteer? I could use two people, to be honest, because then I don't have to do anything. It was great. So do you want to come down? So one of you can be dark matter, and one of you can help me with the masses. So if you come around by me, so what's your name? Jonathan and
Kian.
Jonathan and Kian. So everyone. Great. So what you have here and what you can hopefully see is a big piece of fabric, but let's all, for a moment, imagine this is space-time. So this is what we might call the fabric of the universe. Okay. So our theories of gravity tell us that something with mass, like this galaxy, onto the fabric of space-time causes the fabric of space-time to dip in. And so what that means then is if you were to introduce, say, another mass, it would fall in to the gravitational well of this thing in space-time. Okay? So this is all very well understood, and this is what we'd expect to see for gravity. What we were discussing before, though, is there's more mass there than we think about, right? So if you could come around to Likian. So don't let anyone know, but the secret of dark matter is this bit of string. Is if you could hold that bit of string, but don't let it go, because you'll catapult the mass into the audience and I'll get in trouble. So if you hold that really high, keep holding it, harder, stronger. Yeah, brilliant. So can you kind of see that? So you can kind of see there that actually we don't have a very big mass there, but there's still this deformation in the space-time, okay? So this is kind of what we're looking at the dark matter, is the idea that we look there, we see an amount of mass, but this dip in space-time that we're seeing is much bigger than the mass would account for, okay? So what we're going to move on to discussing is what I called on the previous slide, gravitational lensing. So actually, Einstein tells us that not just massive things are bent by this space-time, also light. So we expect light to move in straight lines through space-time, so you're in charge of light. So if you pull it really hard, but don't let go, keep pulling. Yeah, something like that. Got it? Right, so if you were to roll that now in a straight line, yeah, you can kind of see that the light, you really push it in a straight line. Perfect. You can kind of see that the light went in a curved trajectory, okay? So we can use this to kind of weigh, basically, things that light's passing by. So that's brilliant. So if you can gently release that now. Great, thank you. Brilliant, thank you very much for your help. So we can use this effect basically to weigh objects that are in the foreground of some other distant object, right? So if I have light emitted by some galaxy in the distance passing by some galactic cluster, by measuring how much that light is bent as it passes by it, we can weigh the thing in the middle. And you can end up with really beautiful images like this. So this is termed an Einstein ring. So this is some object in the background of some massive galactic cluster or object here, which has been lensed by this mass effect into some kind of ring. So we can use this to also infer that many of the objects we see out there have more mass in them than we would have guessed from the amount of light and the stars and the hot gas that's there. Okay. One of the really illustrative examples of this is something called the bullet cluster. So this is a an image of a region of space. And these contours are showing the amount of mass, so these regions here in the most massive parts, inferred by gravitational lensing measurements. So this all looks fine and dandy until you overlay the image of the X-ray image of the hot gas that's sitting in the same bit of space. And so what happened in this particular system here is two galactic clusters collided. And as they did so, you can see the characteristic or the name-giving bullet kind of explosion of these two things passing through each other in all this visible matter. But actually, most of the mass is offset from this visible matter. So this tells us that actually most of the mass of these galactic clusters pass through unperturbed by this really cataclysmic event, and makes up most of the mass of the system there. So this is another hint of dark matter as well. We can go back to some of the earliest images we have of the universe through what's called the cosmic microwave background. So this is the light that was emitted relatively soon after the Big Bang. It was at the last, some of the earliest light we have in the universe. And what you can see here in this image is temperature fluctuations. So this light has small temperature fluctuations in it, which is seeded by dark matter. And actually, if we were to plot the power spectrum, so the amount of this difference in temperature as a function of the distance, the angular scale, we'd get something that looks a bit like this pattern here. And this pattern is only explained, and the relative height of these peaks in this temperature fluctuation is only explained if we have the fact that dark matter makes up around 5 times more mass in the universe than normal matter. And then we can go to the biggest objects we have in the universe. So these are called, it's nicknamed the cosmic web. So these are cosmic filaments. So actually these are structures that connect the super clusters of galaxies. So really absolutely the largest things we have in the universe. And these, again, the model for this comes from the fact that we have to have dark matter in the early universe. Okay. So those are all just some of the bits of evidence we have out there for dark matter and why we think there must be dark matter. And from all these bits of evidence, there's some bits we can infer, some information we can infer. So as I said, it makes up most of the universe's mass at about 83%. It had to exist very, very early in the universe to influence things like the CMB, the cosmic microwave background. It doesn't reflect or emit light, otherwise we would have seen it, which is why it gets the name dark matter. We can also, from looking at the motion of local stars, we can work out roughly how much dark matter we expect to be around us in our part of the universe. And that's about 1 proton's worth of dark matter mass every few centimeters cubed. So it doesn't sound like a lot, but remember, most of space is pretty much empty from visible matter. So obviously, in this room, that doesn't sound like very much, but out there, that's quite a bit. And we also know that it's very, very unlikely, actually, it's almost certainly not, any form of ordinary matter. So the only candidate in ordinary matter that it could be is something called a neutrino, but we know that that can't make up the majority of dark matter. The other thing we do know is that it interacts very, very weakly with ordinary matter. So all of the bits of evidence I've shown you so far are from its gravitational interaction with matter, so how it's pulling other bits of visible matter about so we can see it. But we expect and hope that it interacts in other ways with normal matter, which is what I'll come to. So that's all the bits we know, which in the grand scheme of things isn't very much, to be honest. There's a lot we don't know about this dark matter. And actually, one of the big questions is what particle could potentially make up. So, as I said, it's not one of the standard model particles we know and love. It has to do something a bit new. And actually, the parameter space that could explain dark matter spans many, many orders of magnitude, we say here, down from something very, very, very tiny up to a few solar masses. So, a huge, huge range of masses. So I'm not brave enough to try and tackle all that in one talk, so I'm just going to focus on this middle bit in a minute, this middle bit here, with the unfortunately named WIMP candidate. So WIMP stands for Weakly Interactive Massive Particle, which is one of our strong candidates for dark matter, and that's principally what I'm going to talk about for the rest of this presentation. Okay, so as I said, we don't know very much about dark matter in its particle nature, so is there a way we can learn more? So somebody coined these terms, which I think are fantastic ways of describing it. So we can break it, we can make it, or we can shake it. So I'll go through what these things mean. So break it, what we could look for is, as I said, dark matter has to be out there somewhere in the universe. And maybe in some parts of the universe, there's more of it close together than in others. And hopefully in those parts, what we might see is dark matter annihilating with its self, so coming together and spewing out standard model particles that we can see very easily. So for instance, this is just one example of an experiment, and where you can see here dark matter particles annihilating and kicking out lots of standard model particles that we can look for, in this case, high energy particles of light, which we can look for with satellites. So that's the break it one. So we look for standard model particles coming from somewhere out there from dark matter annihilating. We can make it. So I mentioned earlier about the Large Hadron Collider at CERN, which is a particle accelerator. So you can see in this figure here, this is actually the footprint of the Large Hadron Collider under CERN, under Switzerland and France. And what the Large Hadron Collider does is takes advantage really of Einstein's famous equation E equals mc squared and smashes together two particles of very, very high energy. And then because E, energy and mass equivalents, we hope that, or we observe lots of extra matter coming out of that collision. So it's a bit like the idea of smashing together two strawberries and a whole fruit salad coming out. Actually, when I was putting this together, I've used this image many times, but I didn't notice acorns were in the fruit salad before. Don't eat acorns. So we can be a bit more scientific now. Instead of strawberries, we can imagine two particles coming together, colliding. And in that collision, we have all that energy spewed out as new particles created. Okay, so this is what a lot of the work at the Large Hadron Collider is doing, is looking for things like this. And one way of searching for dark matter, though, is to look for an imbalance in this reactor. So instead of seeing nice standard model particles coming out, in every direction, what we'd see is some missing energy in one direction and particles flying out the other direction. This would be a hint that something is there that's carrying off some of that energy. And this would be one way of searching for dark matter that people are using right now. The final way that I mentioned is shake it. So in this way, what we do is, I said that around us is a roughly 1 proton's worth of mass of dark matter every few centimeters cubed. So what we can do is build really sensitive detectors to try and look for that dark matter coming in and bouncing off something on Earth. So these are kind of experiments that you can see here. So I should have had a person for scale, with a person kind of like the height of maybe up to about there from the ground. So these are experiments we can build on Earth to look for dark matter coming in, bouncing off something in the detector, and kicking out something visible that we can see, something like light or things like that. So we'll go into a bit more detail on this kind of experiment. Okay. The obvious question, though, is I said dark matter's out there and it's in space and things, but is there dark matter in the room? So, as I said, local observations tell us that the local density of dark matter is around a proton every few centimeters cubed. And as we're moving about the sun, and the sun is moving about the galactic center, actually in the direction of the Cygnus constellation, and we expect that we're moving through that dark matter halo I talked about earlier. So we're moving about, we're sort of having this dark matter wind blowing in our faces. So if you were to hold out your hand in the right direction, we might expect to have millions of dark matter particles passing through your hand every second. Okay. So as I said, it's in the direction of the Cygnus constellation. So unfortunately, at this time of year, you can't see Cygnus, but if you go out, I think at the end of summer, you'll be able to see Cygnus. If you look that way, you should feel the dark matter wind blowing in your face. Okay, a better picture in the diagrams is something like this, which I think is really nice. So this is the idea that we are going about the sun's going about the galactic center, and this dark matter wind's blowing in our face. So direct dark matter detection experiments are looking for this dark matter wind blowing on Earth in our experiments. Okay. So how does that really work? So dark matter, a dark matter particle is out there somewhere in space, and has been minding its business for a very, very long time until something in our experiment gets in the way. Okay. So that thing gets in the way, and dark matter bounces off it, and the dark matter flies off and carries on its merry way, but the thing it hit in our detector hopefully recoils because of that collision with some energy. And as that recoils, what it can do is it can deposit energy in visible forms in our detector. So it can kick out light by exciting atoms, so we can see light. It can heat up the material, or it can kick out electrons and ions, so it can actually ionize the material. And these are all forms of energy deposition that we're very familiar with detecting. And so we can see these in our experiments. So that's what we're hoping for in direct dark matter detection, this kind of interaction. So now I have to show the obligatory research plot, which is a lot of detail there, but what we really need to focus on here is that the x-axis is the dark matter candidate mass. The y-axis is basically how likely it is to interact. And all the lines on it are different experiments. So basically what an experiment does is it says if dark matter had this mass and it was this likely to interact, then at some statistical confidence level, I would have observed it, and I didn't. So I can draw a line on this graph, which basically says everything above it is excluded parameter space. So if we condense it down just into one line, this kind of summarizes where we stand with direct detection. So the point is that all of this region here has been explored, but you can see this, and some arbitrary plot choices were made here, but you can see that there's some region of space there that hasn't been explored, which we'd like to probe because dark matter could be existing with this mask and this likely to interact, and we just haven't built an experiment that's sensitive enough to see it go. So that's where we're going with direct detection in the future. I should say that there are many, many experiments on here, all using a wide variety of techniques, really creative techniques. I don't have time to discuss them all, so I'll just focus on a few. The one thing I should highlight is there's a few closed bands here, which are experiments which have seen hints of dark matter, but you can see that other experiments have excluded that region. So this is a bit of a mystery to explain these hints. But the main takeaway is that this region has been excluded. So I mentioned there's a variety of detector technologies. So one of the most prolific and successful is what's called a dual phase time projection chamber. So this is a big cylinder filled with a liquid noble gas target, so something like liquid argon or liquid xenon. And what we're looking for there is dark matter particles coming in, bouncing off one of the atoms or nuclei in my target, and it recoiling and producing life. And this detector is read out by some photosensitive detectors above and below, which see that initial flash of light. In that interaction, we also produce some charge. So there's an electric field here which collects that charge and gives me a second flash of light. So this is how this detector technology works. It looks for these two characteristic flashes of light from an interaction in the experiment. So this is it kind of diagrammatically. This is what it looks like in practice. So this is the dark side experiment at the underground lab. Underground lab. And so what you can see here is these light detection modules at the bottom. This part in the middle is this active region here where we're looking for dark interactions. So you can kind of see the scale next to some people there. That's one way of doing it. And as I said, this is one of the most sensitive ways of searching for dark matter. But it's not the only way, and there are other ways which have different advantages. Another way is to use a gaseous target in what's called a spherical proportional counter. So this is a sphere made of metal, which is grounded, and its center has a high voltage electrode. And what we're looking for here is dark matter coming in, same thing again, bumping off a nucleus or atom in our gas, that nucleus recoiling, and this time producing charge in our gas. And then what we do is, because of this high voltage we have here, we draw in the electrons that are kicked out from that interaction, collect them there, and we read out some electrical signal because of that. So this is a completely different way of searching for dark matter, which has different strengths and weaknesses. And this is what it looks like in practice. This is the new G experiment. So this is the big copper ball that I was talking about. This is it when it was being installed into its home in the underground lab in Canada. So these are some of my colleagues there. Okay, so we talked about how much of it we expect to be around us. We talked about how we might hope to detect it. What we didn't talk about is how likely it is really to interact. So I said there are millions of them passing through your hand, hopefully every minute, but the interaction's rare, otherwise we would have seen it already. So we might only expect in one of these large experiments to see a handful of interactions every year. So maybe just a few interactions. Of course, these experiments are made up of many, many atoms, tons of material. So what we're really looking for is a few interactions in this tons of material. So I put a lottery ticket there, but we're scientists, so we're not into just doing that. We design our experiments in such a way that we're really sensitive to detect these kind of things. And so one of the key things we have to do is control what we call backgrounds. So these are things that can interact in our detector in this tons of material that can fake dark matter signals, so they can obscure our ability to search for dark matter. So there are some ways we can exclude these kind of things. So we can do clever analysis techniques. So some of the particles which we might expect to be interacting in our detector, which we know about and are kind of boring for us in dark matter searches, and we can do some clever techniques to reject those, which I'll mention in a second. The other thing we have to do is make our detectors out of very, very pure materials. So oh no, I regret this already. Apologies. You have to sit through the animation again. I mean, it's a good animation. Okay. So in these experiments here, for instance, this copper hole is made of very, very pure copper. Actually, one of the most pure, well, not one of the most pure commercial coppers you can buy, with an ultra pure copper layer on the inside. All the components of this experiment here, again, you see there's lots of copper there. And these plastics will all have been checked for their radioactivity, because any radioactivity in the materials we build our experiment out of can lead to these fake signals in the experiment. So that's one of the other things we do. Strict cleanliness is another thing. So I think if someone had told me when I was going into dark matter research that I'd spend a lot of my time cleaning, I probably wouldn't have believed them. But as any of my colleagues will tell you, strict cleanliness is really critical. So something like a fingerprint on the inside of the experiment will be enough to ruin it. We get a nice calibration peak from all the potassium in the salts and the sweat from your finger. So that will be enough to ruin the experiment. And the other thing we do is we shield the detector from ambient radiation. So I'll show you what I mean by that. So these are just two other dark matter experiments. So again, the NEWSG experiment and this one, the LZ experiment, so LUX-ZEPNER. And you can see the active part of the detector is just this little bit in the middle. Most of the experiment itself is actually shielding. So all of this on the outside here is put there to mitigate mitigate particles coming from the materials the lab is made out of, or you and me walking around the experiment, interacting in our detector and faking dark matter signals, or covering up dark matter signals so they can't detect it. So in the case of the LUX-ZEPNER experiment, you can see that on the outside here, they have what's called a veto. So they have an active region of extra detector outside their main volume, which is looking for interactions. And if they see something there, they say, don't bother me in my detector for a certain period of time. In the NEWSG case, you can see we've got polyethylene, lead, things like that. So polyethylene is to block neutrons. The lead is to block things like photons that come from the rock around us. So I should say that all materials have some intrinsic radioactivity. It's not a problem for you and me, but it is a problem when you're trying to detect a few events per year in many, many, many tons. Okay. So the other thing we need to be careful of is cosmic ray showers. So what do I mean by that? So all the time, Earth's atmosphere is being bombarded by cosmic rays, which is spat out from somewhere very far away in space, or the sun. And these things collide to the upper atmosphere and produce a cascade of particles which rain down all the time, hence the name cosmic shower. So these things are not, as I say, not a problem for you or me, but they are a problem for our experiments. And these things are extremely high energy, so they're extremely hard to shield from. So I'll just, if it hopefully works. Yes, so I can't show you dark matter, but what I can show you is cosmic rays hopefully interacting. So what I have here is called a spark chamber. So actually it's plates of metal with gas in between them. And the plates of metal are at high voltage, so that when a charged particle passes through, like a cosmic ray, you get a track of ionization or a spark through this detector. So I kind of see every now and again you get a little trap or a spark passing through this here. So these are real cosmic rays passing through the room now. So roughly at sea level, there's about one every centimeter squared per minute. So you see here, there's quite a few passing through all the time. And as I said, these aren't the problem, they're completely natural. But with a sensitive experiment, they're the problem. But hopefully you all kind of got to see that. I mean, at the end, if you want to, I can leave it running, you can have a look. Right. So I put a photo there just in case it stopped working, but it all seems to be working today. Good. So as I said, these things are extremely high energy. So they're unlike the other things where I could put lots of lead or lots of polyethylene around my detector to shield it. I can't do that from neons. I would need hundreds and hundreds of meters of rock or something like that to stop it. Conveniently, that's what we do. We use hundreds and hundreds of meters of rock. So what I'm showing on this plot is the equivalent depth under a flat surface in some units of kilometers of water equivalent, which is just some standard units. And the muon flux, so how many of these muons are passing through every centimeter squared per second. And the different points you can see on here are what called deep underground laboratories. So these are labs that you can see are sitting at 2, 3, 4 kilometer water equivalent under the earth or under a mountain to shield experiments from these cosmic rays, because this is the only way we know to really shield these cosmic rays out. And you can see that, as I said, there's about one average of centimeters squared per minute at sea level. You can see down here, we're getting to, less than 10 to the minus 8 per centimeter squared per second. So really, really suppressed this cosmic ray flux. So I should say that the cosmic rays themselves are a problem, but these cosmic rays can hit into materials and spew out other particles, which is also a problem as well. So cosmic rays themselves, as you can see, are quite easy to detect, and so I could veto them, but particles that they spew out are a challenge to cap. Okay, so I mentioned that there's these things called deep underground laboratories. There are many of those all around the world. Of course, in the UK, we're situated about here, but on the North Yorkshire coast, we're actually very privileged to have one of our very own deep underground laboratories in the UK. And it's actually situated at the Bulby mine, which is the deepest mine in the UK. It's actually a potash mine or polyhalite mine now. So I think if this works as well, we've got a nice video that's going down there. So these are just some of the scientists that work at the Bulby Underground Laboratory. This is Chris. So what they're doing now is walking from the science building on the surface towards the shaft to the cage to go down. So they're going down steps, collecting their tallies. So the way that we track whether someone's underground or not, if you're handing an little token when you're going down and you're handling when we're going up. And if they don't have two at the end of the day, something's gone horribly wrong. So they went through airlocks there because this is all pressurized as it forces air through the mine. Okay, and then they're going into the cage. So luckily we don't have to sit through all 8 or 7 minutes of this because that would be very, very boring and dark. But 7 minutes later, you come out at the bottom in a kind of alien world, which is an active salt mine. So this is them coming out. And then it's about a 10-minute walk through these salt tunnels, which you can see here. It's really an active mine. It's very dark. There's no light. We just have a hell on them. This is a walk now to the deep underground lab facility, and the sign which is labelled dark matter, hopefully. So I'm glad it's sped up because we don't want to sit here through all of that.
Sorry, how far is the ground?
Yeah, it's actually 1.1 kilometers underground. Yeah, so there we are. So this is arriving to the lab now, and that's the door. Okay, so we've arrived to the Bulby Underground Laboratory in North Yorkshire. So what does it look like? So as you asked, well, how deep is it? So it's about 1.1 kilometers underground. It has what's called a flat overburden, so the rock above it is flat. Some of these deep underground labs that I was talking about are actually under mountains. So although the lab is actually a few hundred meters above sea level, it still has a kilometer or a few kilometers above it of rock, whereas Bulby is really underground. I'm not 100% sure, so don't quote me, but I'm fairly sure it's the deepest underground flushing toilet in the UK, probably in Europe as well. So there you go. So that's what the facility looks like. When you're inside, it just looks like any other clean room lab that you might have on the surface. So this is a photo inside there, and this is what it looks like schematically. So if you enter through this door here, you have some ultra-pure screening facility here on the left, where they measure materials to check their radioactivity, and this is one of the most sensitive facilities for doing so. And then you have this long area here, which is the experimental hall, where, for instance, we have researchers at Birmingham here, that's me, unfortunately during COVID, she had to wear masks, but this has been one of these small spherical proportional counters that I mentioned before, which we have there for R&D purposes. So that's the Bulby Underground Laboratory. And one thing I should mention is, although this is the clean room part of the lab actually extends well beyond this, and I won't talk about it here, but they do lots of other interesting science at Bulby, aside from dark matter research. So you kind of see there's a little icon there that looks a bit like a Mars rover. So actually they have what's called the Mars Yard X-side, where they test things like Mars rovers, because it's a very hostile environment, lots of rocks and salt and things like that. And I think every year they do run a challenge where you can build a little Mars rover and kind of drive it down. So that's some of the things they do. They also do lots of other research. I mean, it's a very, as I said, it's a very hostile environment, lots of salt. But what we could study there is how life survives in these hostile environments, which is one of the other things to do. One of the other experiments, which is actually involves other people from the University of Birmingham, not myself, is looking at how you treat injuries if you lived on something like lava tunnels on Mars, and again in these kind of harsh environments. So that's the Bulby Underground Laboratory. The Bulby Underground Laboratory has a really rich history, as does the UK in these direct dark matter searches. And this is one of the earlier incarnations of the the underground lab, which looks very much the same as the current one. But actually, a lot of these world-leading detector technologies that I mentioned, this dual-phase time projection chamber, for instance, were pioneered in the UK. And one of them, this is just one of the iterations, is the Zeppelin-2 experiment, which you can now see at the Whitby Museum. So this is on display. So if you're ever up in North Yorkshire and in Whitby, you can pop in and see Zeppelin-2 and read more about it. But as I say, the UK has a rich history of developing these experiments, and we have this fantastic, deep underground lab facility. So we have hopefully a rich future as well with these direct dark matter searches. So in my last slides, I'll just discuss these future dark matter experiments and how we're searching for dark matter in the future. So I've mentioned how we've done it in the past. In the future, we have to get more sensitive to detect dark matter. We have to go beyond, make our detectors more radio pure, more material, more active material in the detector to see dark matter interactions. And two of the proposed experiments which could be cited in Bulby are the XLZD experiment and the dark sphere experiment. So XLZD is a successor of Xenon, Lux, Zeppelin, and Darwin. So the names get more and more complicated, but Zeppelin was one of the ones I mentioned that was pioneered in the UK. So this would be the successor to that some time later. You can see the kind of scale compared to the ones I was showing earlier. This is a person stood next to the experiment there. So here we're talking a much larger volume of material, more like hundreds of tons of liquid xenon in this case. So this is XLZD is a dual phase time projection chamber again. This is the active part of it that would be housed in Bulby. This is all the shield on veto that I mentioned previously that's critical to the experiment's success. The other experiment is dark sphere. So dark sphere follows on from this idea of these spherical proportional characters, so these gaseous spheres for dark matter detection. And the idea there is actually to use some of the research that we've made in developing the new G detectors, which is ultra-pure materials, to actually make our detector just out of this ultra-pure copper. So in this process, what we do is we use the electrochemical properties of copper to basically grow the purest copper you can. So this is down to parts per trillion contamination with uranium and thorium. So really, really pure copper. And to make our detector entirely out of this, which is the sphere you can kind of almost see there. And then surrounded by a thick water shielding to block all the radiation from the lab and the surroundings we get into it. So that's the idea of dark sphere and XLZD. And then just to show again these kind of similar plots I showed before, the bit to take away though is just that the solid lines are kind of where they're sitting in our understanding now in these same plots of dark matter mass and something like how likely it is to interact, called this cross section. The dotted lines are where we expect these two experiments to get down to. So these are, as I say, proposed future experiments that could be cited in this, one of these fantastic facilities we have and we're privileged to have in the UK, which could probe down well beyond current limits. So the UK could once again house one of these really fantastic next generation dark matter experiments. And it's a really exciting time, if you're starting your journey of physics, let's say that some of these experiments would be coming online in the future, in Boston. Okay, so I think we've, if you stuck with me, we went, as I said, from very, very small to very, very big in space to very, very small again, then somehow ended up in Yorkshire. So we started off and we looked at the evidence for dark matter, and we know that the universe is mostly made up of, or most of the mass in the universe, matter, is made up of dark matter. We learned about the dark matter wind, so the idea that we're moving about the sun, or the Earth, we're moving about the sun moving about the galactic center, so we expect to have a dark matter wind blowing in our face. And what we're doing is building really sensitive, What we're doing is building really sensitive experiments in deep underground labs which shield us from the cosmic rays that we could see in the spark chamber over there, and to try and observe this dark matter wave on Earth. And I talked about some of the future experiments to do that, which could be housed in the Bulby Underground Laboratory here in the UK, in North Yorkshire. So, thank you.